going to talk today about the area of a triangle. So let me give you an acute triangle. That's the easiest version. So let's say that this triangle, well, never mind. Let's do a right triangle. Oops. Okay. So we'll do the simple 3, 4, 5 triangle. How do we calculate the area? So formula, area equals 1/2 base times the height. So this particular area is going to be 1/2 times 4 times 3. So you're saying this is the base and this is the height. Everybody agrees? So 1/2 times 4 is 2 times 3 would be 6 units squared, whatever units you're using. Why does that formula work? Close. Half of a rectangle. So Chase said, well, if I create a rectangle, the area of a rectangle is length times width. So this would be length and this would be width. And you'll notice that these two triangles are exactly the same. How do we know they're exactly the same? We can prove it really easily. It has something to do with the right angle. Anybody see a way to prove that those two triangles are the same? Do you guys remember the triangle congruence rules? Side, side, side. Would that work? Well, this equals this, and this equals this, and that one equals itself, so we have side, side, side. What about side, angle, side? Side, angle, side, side, angle, side. That one works. What about angle, angle, side? Well, I know that the top and the bottom are parallel. So those angles, let me be more specific. This angle and this angle are alternate interior, so they're the same, which means that those are the same. So angle, side, angle, angle, side, wait, angle, side, angle. That would work. What about angles? Oh, that's what I just proved. Oops. I just proved angle, side, angle. So angle, angle, side, angle, angle, side. And then angle, angle, angle never works. Doesn't exist. And angle, side, side doesn't exist. Do you remember why angle, side, side doesn't work? Other than it makes Cheyenne giggle. Because that's going to be kind of important in the coming days. Well, if I had a side length, and then I had an angle, so here's a known angle. Let's say it's 20 degrees. And let's say I know that one of the side lengths is 5 feet. And then I'm given the other length. So this other length is, we'll say, 6 feet. That might not be long enough. Okay. Group these together. So, can I make a triangle that works? Right there. Is that the only triangle that works? No. If I twist it the other way, there's another triangle that works. So angle, side, side, the best it can do is narrow it down to 2 triangles. Well, what if that 6-foot side was just long enough to meet at a right angle? Would angle, side, side work? In that case, it would. So there are some cases where angle side side works every time, and there are some times when it doesn't. So if there are two versions, this particular triangle is referred to as the ambig oh boy, ambiguous. How'd I do? This is called the ambiguous case, where you have enough information to narrow it down to two triangles. Whenever that happens, it's called the ambiguous case. It could be this large triangle, or it could be this small triangle. And they both fit the angle side side. So hang on to that because we're going to use it maybe tomorrow. We'll see. Okay, going back to this. So we understand that these two triangles are equal, so if I calculate the area of the rectangle, then I should be able to divide it by 2 and get the area of the triangle, which is where this formula comes from. And it's really easy in a right triangle when you're using the legs as the sides of the rectangle. But what if the hypotenuse ends up being the base? So let me draw the same triangle, just rotate it a little bit. Still a right triangle, 3, 4, 5. And I call 5 the base. How am I going to figure out the area of this? It's 1/2 base times height. Just like it was before. A equals 1/2 base times height. So 1/2 times 5 times, what's the height? Well, the height is right here. That line is called an altitude. An altitude is a line inside a polygon. Well, I guess maybe just a triangle. I'm not sure. And it has two qualities. It connects a vertex to the opposite side. And is perpendicular. Is perpendicular. So if you take one vertex and then you look at the opposite side, you draw a line that connects the vertex to the opposite side, and it hits in such a way that it meets at a right angle. That's called an altitude, and altitudes are the heights of triangles. So how would I figure that out? Well, we have a right triangle right here, correct? So there's a right triangle. I know one of the sides is 3. I don't know the height, and I know that the base, or that one of the legs of the right triangle is less than 5, but I don't know how much less. So I need an angle. Can I calculate an angle? Well, I know the top angle of the big triangle is 90, but I can calculate this angle using trig. What would that angle be? Do you want to hit that door? Lexi, close that. How would you figure that out? Not tangent. Inverse cosine. We know the adjacent and the hypotenuse. So inverse cosine of 3/5 is 53.13. So I now know that this angle is 53.13. Now I can find h. If I focus in again on the little triangle, h is what side in comparison to 53.13? It's the opposite, and 3 is the hypotenuse, so I'm going to use, so sine of 53.13 is equal to h over 3. Excuse me. So 3 sine of 53.13. 3 sine of 53.13. What is that really going to be? The calculator's kind of, oh, well, let me do it this way. Then I won't have that problem. Enter. So 3 sine of the answer. This will be better. Okay, is that what you got? So that's h. Now we can plug h into our area formula. 2.4, 0.5 times 5 times 2.4. And I got the same 6 that I had previously. Okay? What if we had another triangle that was obtuse? Oh, I forgot something. So, I go back to this. Does the rectangle idea still work? Is that triangle half of a rectangle? Which rectangle? What's that? So if I were to draw a rectangle around this, how would I draw it? Okay, let's try reflecting. That's a good idea. So let's flip this up, down. Oh, oops. Let me draw a better triangle, because that's not a very good one. So it's a right triangle. Okay, so let's flip this so it's horizontal. Clone it. Now I want to flip it. And then I just got to rotate a little bit, right? Does that make a rectangle? What do we call that? That's a kite. So if you flip it across the hypotenuse, that doesn't work. Right? And if I flipped it, now I flipped it again the other way. Okay. Does that work? Yeah, so if you flip it twice, you flip it vertically and horizontally, then you'll end up with a rectangle. Does anyone see another way to do that? With less flipping? Or no flipping at all? Oh, you're saying just draw a line parallel to this, and then a line parallel. That works. Tristan? Well, we have a base and we have a height, right? So we should be able to make a rectangle with that base and the same height. So but is that triangle half of the rectangle? This is what Josh was saying. How do you know? These two areas are the same, and these two areas are the same. So the rectangle is two big triangles and two little triangles, and the right triangle that we're looking at is one big and one little. So that works. Okay. Now let's look at an obtuse triangle. So, if this is the base, where is the height? So if we follow the rules of an altitude, we need to pick a vertex. There's a vertex. And here is my base. And the vertex is perpendicular to the base, but there's a problem. The base is not long enough. So we extend the base, and then we drop this down. So there is my altitude. Let's call the base 6, and we'll call the height 4. What is the area of that triangle? 4 times 6 is 24, divided by 2 is 12. Where's the rectangle? Pointing doesn't help. You were drawing it in your head, I know. The end of what? So from the end of the base on the right side, going up, okay, and draw this parallel to the base. Where's the rest of it? So on the altitude. So here. Is the triangle half of that rectangle? No. It's less than. Why, Chaseley? Well, we don't know how big that is. But the area of the rectangle should be 24 because it's base times height. Right, so we need to end the rectangle right there. Now here's a fun part. How do we know that that triangle is half of the rectangle? Just because won't get you any points on the test. It also doesn't work with my children. They try it all the time. Anybody see a way that we could prove that that triangle is half of the rectangle? Okay. Can I give you a hint? So this much is taken care of. Now what do we need to show? Right? So you see what I've done? I've created a rectangle, and the triangle is half of this rectangle. So we can ignore that. So all we have to show is what? Wait, be more specific. The top thin rectangle, so we'll call this area capital A, has to be not the same area as the triangle. It's going to compare to the triangle in what way? It needs to be double, right? So little a needs to be half of capital A. Because I don't know anything about that rectangle on the left side, right? This rectangle over here is totally unknown because I have no idea how long its base is. I know its height, but the base, I don't have any idea. I would need an angle or another measurement somehow to figure that out. What's that? Yeah, I don't know how big that is, but I know it's twice as big as A. Okay? So if I could figure out a triangle, let's say, oops, if I could show that this and this are the same size, then I'm done. Maybe I'll leave that for you for an extra credit. How about that? If you can prove it, I'll give you extra credit. And it doesn't even have to be a formal proof. An explanation is enough. So if you can prove that this remaining little a is half of capital A, I'll give you extra credit. All right. So what if we don't know any side lengths? All we have is some random triangle. Oops. Actually, maybe I'll show you this first. Just sit right there. Test is 100. Yeah, for now. Okay, let me show you a geometer sketchpad thing that's kind of neat to know. I don't think so. Okay, I have a line, and I'm going to create a parallel line, And then I'm going to construct a triangle on here. Sorry. So there's my triangle. I can move it, change its size. For the rectangle, there's a rectangle. And this program is really nice because you can calculate areas pretty easily. If I draw the rectangle, definitely want to change that color. Draw the triangle. That'll work. So here's the rectangle. Yeah, I do. And here's the area of the triangle. And if I calculate the rectangle divided by 2, notice they're the same. These two values are the same. And no matter how I move this, they're always going to be equal. That's simple enough. Maybe. So maybe we can merge those. Won't let me. All right, well, if I calculated the altitude, so from here to here, then I could take the length of the base and the length of the height, and then I could calculate base times height divided by 2. I get that same value. But what I wanted to show you is, notice how if I move this point along the top, nothing changes. Any triangle that lies on the same base and has a point parallel to the top of that rectangle will have the same area, no matter where you move that. I can go way off the screen and the area doesn't change. As soon as I change the height, all those numbers change, but they all end up being the same. These three values are the same, but if I move this point along the parallel top, the area does not change. Okay, so let's look at a random acute triangle. It's not the one I wanted. I'll just draw one. So there's an acute triangle. We'll just label the sides A, B, C, little a, little c, and little b. How would I calculate the area of this triangle without knowing any values, including the height? So our formula is 1/2 base times height. Well, I know the base in this case is little b. So let's call this the base. So 1/2 b times the height. Well, the height is an altitude. Can we figure out what the formula is for the height? Well, let's call this h. How did we do this in a problem a couple minutes ago? In this right triangle, how would I calculate h with the given information inside that triangle? Not cosine. So if I call a theta, c is a known side, how would I calculate h? And I have to use angle A. It's not inverse. We're not looking for A, we're looking for H. Sine of A, the sine of A equals H over C. So solving for H gives me sine, or C sine of A. Okay, this is really important that you get this part. This is going to be on your worksheet. Does this make sense? So we have a right triangle. I know the hypotenuse, and I'm looking for the opposite side. So the only angle that I can figure out inside this triangle would be A. I would need to know A in order to calculate anything. B isn't going to help because this triangle is a portion of B. C doesn't even come into play in this triangle, so we ignore it altogether. So the sine of A is the height over the hypotenuse, so H over C. Solving for H, I get H equals C sine of A. So I plug H into the formula, and I get 1/2 B C sine of A. Now, hang on a second. What if I rotated this triangle? Okay. So what if I moved my base up here to little a? Now my altitude is going to look like this. That's not a very good altitude. So this is, so 1/2 A times, well, if I look at angle C, sine of C equals height over B. So you're going to plug in B sine of C, capital C. I'll write that over here. 1/2 A B sine of C. And what if I moved my base over here to little c? So this is going to go away. So the sine of B is equal to H over little a. So A sine of B. So 1/2, and it's actually CA sine of B. But I'm going to change the order of A and C. What do you notice about all three of those formulas? They all use sine. What do you need in order to calculate the area of a triangle? You have to have one angle. Does it matter which one? No. But if you have one angle, what else do you need? The two sides that create the angle, or the two adjacent sides, which is kind of strange because in a right triangle, one of them would be a hypotenuse. Well, unless you were talking about the right angle. So if I know angle A, then I need to know C and I need to know B. And I could do C 1/2 C times B times the sine of A, and that would give me the area. Okay? Why not something like this? A times C times the, it would be cosine of C. Why wouldn't that work? Or wait, let's do, hold on a second. A C cosine of A. Oh no, that'll work. What's wrong with that? Why would AC cosine of C not work? So if we called C the base, well, no, we'd have to call this the base. Here's the right angle. Here's C. If I know capital C, and I knew A, then this would be, oh, that would still be sine. Anyway, sorry, that's not going to work. I forgot how to make it up, but you can create one so that instead of side angle side, you can create one that's angle side side. But the trouble is you run into the ambiguous case. So we always use sine in our formula. There is a way to use cosine, but then you run into the ambiguous case. So don't ever use the cosine for the area formula. What's your question? Oh, we'll give him 5 points. Do you know what the answer is? Yes. Yes. Okay. So, I gave you a triangle, said this is 20 degrees, this is 18 feet, and this is, I don't know, 12 feet. How would I calculate the area? Well, 1/2 times 18 times 20 times, or no, sorry, 12, sine of 20. So you need an angle, and you need the two sides that create the angle. So 1/2 times 18 times 12 times the sine of 20. So 1/2 times 18 times 12 times the sine of 20. The area of this is 36.93 square feet. Does it matter? No, it doesn't. Because multiplication commutes. So it would work either way. Yes. Give him half. Okay. Let's do a right triangle. So what's the complement of 53.1? 36.9. Now it shouldn't matter which two sides and which angle we pick. So as long as you have a side angle side, it should work. So 0.5 times 5 times 4 times the sine of 53.1 should be equal to 0.5 times 3 times 5 times the sine of 36.9. What did I... Oh, I got my angles backwards. Thank you. 53.1 and 36.9. Okay, let's try that again. So 0.5 times 3 times 5 times the sine of 53.1. That should equal 0.5 times 4 times 5 times the sine of 36.9. And those are off because the angles have been rounded. How would you do the other one? Times 3 times 4 times sine of 90. So all those are the same. And again, I rounded the angle, so it's a little bit messed up. So that's most of your worksheet, is just calculating those. But that's super easy. Any questions on that? That was a really long way to explain how to do that, right? But it's a good explanation because it'll help for tomorrow. Okay, let me remind you of something else. If I had a triangle, well, and we're going to talk about more than just a triangle. Does anybody know what a regular polygon is? What does it mean to be regular for geometric shapes? So regular polygons are equilateral. Equilateral means all of the sides are the same length. They're also equiangular. Angular, which means that all the angles are the same. So, a regular triangle is called an equilateral triangle, and it just so happens, if it's equilateral, it's automatically equiangular. What is the angle sum of this triangle? 180. What is the size of each angle? 60. Now, this is only true on a flat surface. It's not true on the Earth. It's not true in the hyperbolic plane. What do we call a regular quadrilateral? A square. What is the angle sum of a square? 360. And how big is each angle? 90. Now we're going to test my art skills. A regular pentagon. What is the angle sum of a pentagon? Is that the angle size you're saying is 72 or the sum? What did you say? 520? Close. It's 540. How come? Well, a better question is, why is a square 360? 4 90-degree angles, but could we use the definition of a triangle to find out the angle sum of a square? Well, what you do is you pick any vertex, doesn't matter which one, and you draw all of the diagonals. A diagonal is a segment in a polygon that connects a vertex to a non-consecutive vertex. So if a segment connects vertex to a consecutive vertex, that's called a side. If a vertex is connected to a non-consecutive vertex, that's called a diagonal. So this is two triangles. Well, each of those triangles has an angle sum of 180. Right? So if you look, these two triangles have 1, 2, 3, 4, 5, 6 angles. And those 6 angles add up to be 4 right angles, so the angle sum is 360. So in a pentagon, you just pick a vertex and draw all of the diagonals. And each one of those triangles has an angle sum of 180. So what is 180 times 3? So the sum is 540. How do we calculate the size of each angle? Divide 540 by 5 equal angles, and we get each angle is 108. Okay? So if I drew a hexagon, and I draw the diagonals, there are 4 triangles. So 4 times 180, what is that? What is it? 720, and I'm going to divide that by 6, which is 120. Okay. What about a decagon? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Beautiful. Actually, I think I can steal one from. Watch this. I can cheat. On what? I didn't write that. Let me see it. Just the same. No, just the same as everybody else. So there's a decagon. How many triangles are going to be in a decagon? Well, let's compare. What's the comparison to number of sides to number of triangles? 3 sides, how many triangles? 1. 4 sides, how many triangles? 2. 5 sides, how many triangles? 3. 6 side, how many triangles? 4. So I should be able to draw 8. 1, 2, 3, 4, 5, 6. Was that not a decagon? Oh, but now I drew 7 lines, so there are 8 triangles. Which makes sense, because you create a triangle with every vertex except the 2 consecutive vertices. So this is going to be 10 times 180, which is 1080. No, 8, sorry. So it's going to be 8 times 180. What is that? 1440. And I divide that by 10, so 144 degrees in each angle. Now, if you don't like that method, there's another method. Right? If you take a particular side and extend it, then it creates what is called an exterior angle. If you do that with all of the sides, then you get exterior angles that are all the same size. So we could do that here, 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 and here. And then from the pentagon, that one, that one, that one, this one, that one. And for some reason, which is provable, but I'm not going to do it, the exterior angle sum of every polygon is 360 degrees on all of them. So you can figure out how big each exterior angle is by just taking 360 and dividing it by the number of sides. So for my decagon, this angle here is going to be 360 divided by 10, which is 36 degrees. Well, if the exterior angle is 36, how do we find the interior angle? 180 minus 36 will give us this angle as 144. So on the worksheet today, you need to be able to calculate the angle, the size of an interior angle. Okay? So let's focus on the pentagon. The interior angle of a pentagon is 108. Now this is where this gets tough, so if you get confused, please ask a lot of questions. If I had a pentagon, regular, and I told you that the perimeter was, 100 square centimeters, or just centimeters, 100 centimeters. And I asked you, what is the area? Now we'll work a couple of these, but they're pretty intense. Okay? Well, okay, so each side is 20. Let me write that. And what else do we know? The base of what? Which triangle? So if I drew these, well, we know these two are the same size. Can we prove that this one is also the same size? And I don't even know if that's true. Well, if it was true, when we'll find this out in a minute, this angle is how big? So 360 divided by 5 is 72. 72 is the measure of an exterior angle, so the measure of the interior angle would be 108. So this is 108. So let's see if 1/2 times 20 times 20 times the sine of 108, and what do we need to do to that? We need to triple it. That's assuming that these three triangles are the same size, which I'm not sure they are. We'll find out in a minute. Okay, let's look at this a different way. Oops. Let's focus in on this triangle. I hope this is right. This would be really nice if it works, but I don't know that it does. So that's 570.63 cubic or square centimeters. Okay, what do I know about the triangle that I just drew, besides its base is 20? Do I know the measure of its angles? They're both half of 108. So both of these angles are 54. Because if I draw that line straight across, that's an angle bisector, because it hits the midpoint of the opposite side. So that's 54. So can I calculate H? Well, this triangle here, let me draw it bigger. I know the angle is 54. I know this is a right angle. The base is 10 because it's half of the side of the pentagon. So this is, if I'm looking for x, this is going to be what kind of problem? Tangent problem. So the tangent of 54 equals x over 10. So the height, h, is 10 tangent of 54. Everybody follow that? What is that number? Well, and I'll probably need it in my calculator, so 10 tangent of 54 is that. So now I can calculate the area of this. Times it by 20, and then 20 would be the area of the rectangle. So I'm going to times this by 10 instead of 20. Does everybody agree? I take this value here, which is 13.76. Oh, I forgot to divide it, didn't I? Okay. I need to divide this number by 2. No, I don't. 10 tangent out of 54. So that's the height. Are you running into problems? You're in radians for some reason. Go back to degrees. There you go. Probably. So 10 tangent of 54, 13.76. So that's the height. To find the area of one of these little rectangles, times by 0.5 and times by 20. Everybody follow there? So 137.63. Now what do I need to do? Now there are 5 of those. So if I were to draw all of those, you see that there are actually 1, 2, 3, 4, 5 of those triangles. times by 5, and we were wrong to begin with. That number is not the same as this number. But the area is 688.19. Now, would you like to see another one? We'll do one more. Okay, so let's pick, here's a heptagon, and let's say that the area, the perimeter of the heptagon is 343 inches. So that's perimeter. How long is each side? 49. So this is 49 inches. And I draw this triangle. So remind me again how to calculate the interior angle of a heptagon. 360 divided by 7. 360 divided by 7 will tell me that angle. Okay, so 360 divided by 7, 51.42. So if I do 180 minus my answer, my interior angles are 128.57. So now in the little, I guess that's like a pentagon slice of pizza. If I calculate the area of this slice of pizza and times it by 7, then I get the whole area. Well, I know that the angles, the base angles of this isosceles triangle are half of 128.57. So divide that by 2. So those are 64. Let me draw that bigger. So this is 64.28. And I know the base is 49. I need to calculate the height. This height here. Well, in the little triangle, this would be 24.5. And I'm looking for x. It's still tangent. So it's the tangent of 64.28 equals x over 24.5. 24.5 tangent of that angle. That gives me a height of 50.87. Now how do I calculate the area of my slice of pizza? So 0.5 times 50.87 times, not 24, 49, because I want the area of this. So I'm going to multiply the 49 by this 50.87 and then divide it by 2. So that's the area of one slice of pizza. Now what do I do? Times that by 7 slices, and my area would be 87.25. And it's going to be the same process on every single shape, just the number of sides changes, so you need to recalculate the angles. But it's always going to be tangent of half the angle equals x over half the base. That's always going to happen. And then you just multiply it by how many slices you have. Okay. So there are 2 worksheets up here. The first one is a piece of cake. The second one, 2/3 of it is really easy. And then the back side, you have to do some of these areas. Do you want to read? Hold on a second.